I believe that the biggest source of confusion for quantum mechanics is actually wrong comparisons with classical mechanics. It goes like this. First, reduce classical mechanics to a cartoonish version. Second, compare that to quantum mechanics. Third, conclude that quantum mechanics is totally different from classical mechanics. Well, yes, different from the misleading portrayed version of classical mechanics. If you set up the comparison well, so that you're comparing apples to apples, two things happen. First of all, quantum mechanics becomes less weird, and you can use the classical intuition to understand a good chunk of it. Second, you can pinpoint exactly where the difference comes from and get a better understanding of both. So let's see what I mean. The standard way to compare the two is the following. The state of a classical system is given by position and momentum. The state of a quantum system instead is given by a wave function. So a classical system has a single well-defined pair of position and momentum. It's always at a precise location with a precise speed. A quantum system instead has a probability distribution. It's never in a single precise location. Classical systems are therefore point particles, while quantum systems are probability waves. And therefore, they are completely different objects, they're weird, we can't really understand them because we don't live in the quantum world and so on. What I'm telling you is that this picture is very misleading. And whenever you hear claims like this, you should think critically for a bit. So a classical object has a single well-defined position and momentum. Well, is that really true? What are examples of classical objects? Let's say we use classical mechanics to describe planetary motion, so the Earth would be a classical object. We use classical mechanics to describe volumes of gas, so a balloon. And a person, such as yourself, is also a classical object. So what's the single well-defined position of this object? Is it this, or this, or this, or these? Which one is the single true position? Clearly, there is no single true position. All these objects extend in space. Similarly, there is not going to be a single velocity. If you wave your hand, part of your body will be moving while other will be standing still. So this idea that classical objects have a single well-defined position and momentum is clearly patently false. Okay, so how do we make the comparison? Well, the state of a quantum system is a wave function. What about the classical system? We saw that it is not fully concentrated in a single position of momentum, so a classical system is a distribution over position and momentum. At each possible position and momentum combination, we will have a density that tells us how much of the system is at that position and that momentum. Note that they're still different objects. One is a real function over position and momentum, the other is a complex function over position alone. But they have things in common. We can integrate them and they must integrate to one. But you may say, wait a minute, in many cases we do use only position and momentum. How does that work? What happens is that when the size of the objects are small compared to how far apart they are, like in the case of planets, we can pretend all mass is concentrated in a single point, the center of mass. But here's the thing, both classical mechanics and quantum mechanics have a well-defined center of mass. The position and momentum of the center of mass is the simple average in classical mechanics. In quantum mechanics is a little bit more complicated, the expression is different, but conceptually they're the same things. So even quantum systems have a well-defined position and momentum, that of the center of mass. So classical systems are distributions, like quantum system, and quantum systems have a well-defined position and momentum for the center of mass, just like classical systems. They're not that different in that respect. So now that we have a proper comparison, we can go through a few things and gain more insight. First of all, we can see that eigenstates exist in classical mechanics as well, and they are much easier to understand. So x is our position operator, just like in quantum mechanics, and an eigenstate satisfies the following expression, x times rho equals to x0 times rho, where x0 is a specific value for the position. Now suppose we evaluate the expression at x0. Then on both sides, rho is multiplied by x0. So rho can be anything at x0. Now suppose you evaluate the expression at another point, say x1. Now you have rho multiplied by x1 on one side and rho multiplied by x0 on the other side. The only way that the equation is satisfied is if rho is 0. So the equation means that rho is 0 for all x's that are different than x0. In other words, the distribution is all concentrated at x0. The support, the region where the function is different than 0, is exactly this line. So the general solution is a product of a delta Dirac centered at x0 times a distribution over p. So what is an eigenstate? An eigenstate of position is not just a distribution that fixes the expectation value of position, it's much more constrained. It fixes the value of position for each element of the distribution. All the elements of the distribution have exactly the same position. All the elements of the distribution are concentrated in a single value. Now this works for all observables. An eigenstate for the harmonic oscillator, well, it's a distribution constrained over the ellipse given by the energy. So it's not that the average energy is fixed, it's that all the elements of the distribution have exactly the same energy. Eigenstates work in the same in classical and quantum mechanics, except that in classical mechanics they are much easier to understand. Naturally, there are going to be differences. In classical mechanics, you have eigenstates of both position and momentum. You can have the product of two delta Diracs in position and momentum. Well, at least mathematically, physically, they don't make much sense. In quantum mechanics, you can't, because a delta Dirac in position is already a uniform distribution in momentum. But see, the difference is in what eigenstates you can have, not in whether or not you can have them. In both cases, you have a distribution. In both cases, an eigenstate fixes the value of a quantity for all the elements of the distribution. In this respect, they're not so different after all. Now let's see how this perspective helps us debunk a particular misconception, that quantum mechanics does not follow classical logic. It goes like this. Consider two regions of phase space A and B. And consider these three statements. The state of the particle is in A, is in B, or in A or B. And in classical mechanics, all statements can be true or false. And the third one is true if and only if one of the first two statements is true. So the particle is going to be in the region A or B only if it is in A or if it's in B. Now let's look at the quantum case. In the quantum case, you have the uncertainty principle, so that the area given by delta x and delta p can never be smaller than h bar over 2. Now suppose each region is h bar over 4. So that the composed region is h bar over 2. The first two statements are always going to be false because of the uncertainty principle. But the third one can be true. And it will be true even if the first two statements are false. So A is false, B is false, and A or B is true. This means that quantum mechanics does not follow classical logic. Quantum mechanics needs a different logic. As before, when you hear a wild claim like this, you should think critically. Let's look more closely at the setup. As we said, planets, balls are not point. A classical system is a distribution. When we say the state of the particle is in A, we can mean two things. One is that the center of mass is in A. In this case, it is certainly true that A or B is true only if either A is true or B is true. But we could also mean that the whole system is in A. Now, if A is true, then the distribution outside of A is 0. If B is true, then the distribution outside of B is 0. But in this case, A or B can be true if the system, for example, is half in A and half in B. But if it's half in A, it does not mean that the whole system is in A. And if it's half in B, it does not mean that the whole system is in B. So we can have that A or B is true, while A is false and B is false. And there is no surprise here, because logically joining the region is not really the logical OR. Both of these cases work exactly the same in classical and quantum mechanics. So classical and quantum mechanics follow the same logic, once you compare apples to apples. If you use the center of mass case in classical mechanics and the whole distribution case in quantum mechanics, then of course you're not comparing apples to apples, and they do follow a different set of rules, but that's just the problem, that you're mixing different things, not that classical and quantum mechanics are different. Okay, so we saw that making the right parallel helps us understand how some things are the same, like the eigenstate in both classical and quantum mechanics, and how we can solve paradoxes, like the idea that quantum mechanics seem to violate classical logic. Now let's see how we can understand some of the differences. As we said, classical systems are distributions. But in classical systems, we can distinguish two radically different types of distribution, whose physical meaning is different, but the math is the same. The first one is what I call a statistical distribution, where the matter is really spread across space. That's what we had in mind when we were talking about an object like a planet being distributed in space. 50% of the mass is in a particular region and 50% of the mass is in another region. Another type of distribution is a probability distribution. Here we can think of the mass as concentrating in a point, the center of mass, but for example it jumps around. So imagine a speck of dust undergoing Brownian motion, it moves chaotically. So it's not 50% of the mass is in a region, it's the whole system will be in a region 50% of the time. Now in classical mechanics we can distinguish between these two. We can tell whether it's a part at some position, as in the statistical distribution, or whether it's the whole jiggling around, as in the probability distribution. We can do so because in principle we can interact with parts of the distribution, parts of the classical system, to reveal their nature. We can distinguish between parts staying still in a region from everything moving in and out of the region. Now, in quantum mechanics, we can't do that. This is going to be a recurring theme in all my videos. We can't study what the parts of the system are doing. So we cannot distinguish between the statistical and the probabilistic case. These two types of distribution merge into one. We have a system distributed in space, but we can tell whether it's an evenly distributed system or it's clumped and jiggles around. Maybe it's partly distributed, maybe it's partly jiggling around. This is where quantum mechanics is radically different. We can't tell these two cases apart. And note that the first case, the one that the system is physically spread, it's the wave nature of quantum mechanics. The system in some cases behaves like it's in two places at once. The electron seems to pass through both slits and interferes with itself. The second case, the one where the system jumps around, is the particle nature of the quantum mechanics. The system, in some cases, behaves like it's all in one place, taken at random. We measure position after the slit, and the particle as a whole is found in one place. Hopefully you can see how we can more exactly put the finger on what's the difference between classical and quantum mechanics, see where it comes from, and make sense of it. This does not remove at all any of the interesting and counterintuitive consequences, but at least to me, it gives me a sense of why we have them. It makes sense to me, and hopefully it makes more sense to you. So let's recap. A lot of confusion in quantum mechanics comes from misleading comparison with classical mechanics, where we typically compare a full distribution in the quantum case with just the center of mass on the other side. If you compare apples to apples, distribution to distribution, and center of mass with center of mass, things make a lot more sense. The mathematical intuition from one can partially transfer to the other. You can see more clearly what is the same or what is different, which helps make quantum mechanics less weird and more intuitive.